Hello, everyone. Welcome back, everybody. Today in geometry, we will look at something called analytic geometry. What that means is it's basically another way of proving all the stuff that you've been doing, but without having to do all the nasty work of statement and reason. Basically, using the coordinate stuff that we've been learning so far, using the XY axes, to prove all the theorems that we have, making things a little bit easier, hopefully. As I said, this is going to be a section on proving using analytic geometry. And we're going to go ahead and look at a few problems just so you can get the idea as to how it actually works. Now, in this first example over here, what I want to do is I want to prove that the diagonals of a parallelogram bisect each other. This is something that we proved in the past, back in chapter 9, if I remember correctly. And the proof of it wasn't really too bad. But let's just say that, we want to prove this to somebody that is an algebra student that doesn't formally have all the geometry training that we did. So we're going to go ahead and use the coordinate system. So you can see on the right-hand side, we have an axis, which we're going to set everything up. Now, for all of these proofs, there are three simple rules that you should always try to follow, okay? Rule number one is that you want to try to keep everything positive if possible, meaning that if you can do it, all your coordinates should be in the quadrant one, where both x and y are going to be non-negative, because as soon as you deal with negative numbers, that makes things a little bit nasty. Since we're dealing with geometric shapes, it doesn't make sense to have any kind of length to be negative, so that's why we try to stay away from the other quadrants then. Next, try to use the origin or the axis or an axis in some way or another, okay? So whenever you try to draw, like, say, a certain shape, like in this case, we're going to try to draw a parallelogram, we're going to try to utilize the origin, because 0, 0 is something that is nice and simple that we can work off of. In addition, maybe using either the x-axis or the y-axis, and maybe sometimes you can use both. Just so that you can have, like, say, a horizontal line, which is also kind of nice too. And finally, the last one is to minimize the number of variables that you're going to be using here. Since we're not going to use actual numbers besides zeros, we're going to be looking at variables. It might be nice to kind of just, make it no more than like 2 or 3 variables, because we might sometimes have to solve for them. All right, anyhow, let's go ahead and try this problem right here. So let me go ahead and set up the following thing. Prove that the diagonals of a parallelogram bisect each other. So first things first, I need to basically draw a parallelogram according to what we have. So parallelogram by definition means that we're going to have 2 pairs of opposite sides that are going to be parallel to each other. So one point, as we said, is going to be 0, 0 over here, which I'm going to go ahead and denote as A, because again, always try to use the origin as a starting point just to make things a little bit easier. Now, the next thing that we said is that always try to use an axis also. So in this case, why don't I go ahead and use the x-axis? So over here, maybe I'll have another point over here. Let's go ahead and say that that is going to be a comma 0. Okay. So let me go ahead and change the name of the point over here, because I'm using a and I don't want to mix that up with the lowercase a that I have over there. Then afterwards, let's go ahead and introduce our third point. Now, our third point in this case is just somewhere out there, because we don't know what's the length of this parallelogram, but we just know that it's like somewhere diagonal of the origin. So somewhere out here, we're going to go ahead and call it B comma C, because we don't know anything about the x coordinate, nor do we know anything about the y coordinate. We have to introduce new variables in this case, so that's why we have to use B and C, because you don't know if there's anything relationship, if you don't know if there's any kind of relationship between A, B, and C for the time being. Now that final point over here, keep in mind that this is going to be parallelogram, right? And as much as I would like to say that this is going to be D comma E, we don't actually want to do that, because remember, we want to minimize the number of variables. We know that it's a parallelogram, so that means that this last point over here, I like to think that it's a little bit more closer related to what we have over here. Notice that, remember, the two opposite sides are going to be parallel to each other. So if you look at the bottom part right here, which is horizontal, then that means that this part right here should also be horizontal. And because it's horizontal, then that means that your slope is going to be 0. The length of it, according to what we have over here, is supposed to be A. So that means the length of this part right here should also be equal to A. So in terms of our coordinate, that is going to be b comma, actually, I'm sorry, it's going to be, let me go ahead and use red in this case right here. It's going to be b plus a, because we add a length of a to x. And then the coordinate of y is going to be c, because remember, the bottom part is going to be horizontal then. So there it is. That is going to be our first setup right there. And that is going to be our parallelogram. Now, if you want, you can go ahead and give some coordinate names if you want. So let me go ahead and name it then. Let's go ahead and say W, X, Y, Z, or RSTU. I think that might be a little bit better because I don't want to use X in this case. So let's go ahead and say R, S, and then T, and then U. Okay. Now, according to this, I need to basically show that the diagonals are going to bisect each other. So what that means is, in terms of what is it that I need to show, I need to show that the midpoint of US, the line segment, is going to be the same thing as the midpoint of RT, the line segment. Okay, so that is going to be what I need to show. If I can somehow show that according to my coordinates, then we're pretty much good to go then. All right, so let's go ahead and start with the first piece. Let's go ahead and start with RT over here. Okay, let's go ahead and start with RT over here. So the midpoint of RT, according to what we've learned about like how to solve for the midpoint, remember, it's going to be the middle of the x values and the middle of the y value. So midpoint theorem, we basically went through that, right? According to that picture then, it's going to be b plus a and then plus 0 over 2. And then for the other one, it's going to be c plus 0 over 2. So if we were to clean that up, that is just simply going to be b plus a over 2 and then c over 2. Now, what I'm going to do is I'm going to go ahead and solve for the midpoint of u and s over here. And if it's the same thing, then we're pretty much done then. So the midpoint of us is going to be, again, the average of the x values. So that's a plus b and then over 2. And then comma for the y value, it's also the average of the two. So it's c plus 0 over 2. So that, if I clean it up, is a plus b over 2 comma c over 2. So therefore, it's the same thing, and that means we're done. Okay, so note it's the proof. It's really, really simple for the most part, so long as you keep things, well, I guess simplified. So long as you don't make it more complex than it is, then you should be fine. Also, try to do your best to follow these rules, and then your your proof will be pretty straightforward. All right, let's go ahead and try to do another one. Okay, in this case right here, I want to say prove that in any triangle, the line segment joining the midpoints of two sides is parallel and 1/2 as long as the third side. Again, this is a theorem that we proved in the past, which I am going to bring to light using this coordinate geometry. The way we proved it a long time ago, it was pretty intensive, actually, if you remember correctly. What we had to do was we had to create some sort of parallelogram that looks like this, which is going to contain two congruent triangles, and then afterward bisect it, and so on and so on. And it was really big mess. I think the proof took about 15-20 minutes. Well, maybe it's a little bit shorter than that, but nonetheless, it was a pretty lengthy proof. So what I want to do is I'm going to go ahead and use coordinate geometry over here just to prove it, to see if it's any easier. So once again, keeping in mind the rules, right, of what we said, or the strategies, we're going to go ahead and use the origin. So that means we're going to use 0, 0. Now, next, I'm going to go ahead and pull out the other points over here. And that, according to what we said earlier, is going to be A0. Nothing has changed since the last one. And then the last point, in this case, because we have a triangle that we're trying to set up, is going to be over here, and we don't know anything about it. So we're just going to go ahead and call that B, comma, C. So right there, that is going to be our triangle. Now, let's just make it a little bit more scaling, because then, according to this, it doesn't look like it's going to be an isosceles triangle then. So I'm going to go ahead and draw it somewhere over here. And I want to show you also a new tactic also, just in case. Rather than calling it B, comma, C and A, comma, 0, let me do the following. Okay, and this is always a trick that you can also use. I am going to call this coordinate over here 2B, comma, 2C. And then the bottom one over there, I am also going to change that so that it's going to be 2a. And the reason why I'm doing that is, well, in this theorem right here, or in this proof, we're calling for the midpoint. And so if you create coordinates that are doubled, then the midpoint is going to be something that is going to be a whole number rather than something that is a fraction. So this is something that you can, strategize to make things a little bit easier for you. Now, if you want to use b comma c and a, that's totally fine. You're just going to end up with something that's over here where you're going to have fractions. But if you don't like fractions, then you can just go ahead and do what I did. And hopefully if I scroll back down, the lines are over there. All right, so here it is. Let's go ahead and give some names to these coordinates once again. So let's go ahead and say that this is r, and then this is s, and then this is t. So what I need to do now is, once I have all of that, let's start pulling out all the other stuff. Now, it says that I want to take the midpoints of each of the sides. So the two sides that I'm looking at to show parallel to would be RT and TS. Those are probably the two easiest sides to work with, okay? For those two sides, RT and TS, we're going to go ahead and pull out their midpoints. So over here, we're going to go ahead and draw the midpoint. Over here, we're going to go ahead and draw the midpoint. Now, just like before, we're going to go ahead and give them names. And because they're midpoints, then that means that we can assign them specific variables, just like we did with R, S, and T. Now, not necessarily new variables, but the old ones that we've been using so far. So for example, over here, this guy right here, if it's the midpoint, thinking about what we have according to the picture, it should be B, comma, C. Okay, so that should be B, comma, C because you're using the midpoint between RT, so you're using the midpoint rule. Give it a name if you want. We'll go ahead and call it M. Then for the other one, according to what we have in the picture, it's supposed to be the midpoint there. So that is going to be 2A plus 2B divided by 2, comma 2C divided by 2, and then also plus 0 technically. So that right there, if we want to clean that up a little bit, which I think we should, is going to be A plus B, comma C. So note how, again, in this case, when we solve for the midpoint, it's something nice and clean and not something with fractions. So let's go ahead and call that N right there then. All right, now that we have everything set up according to what we want, which is a triangle, calling out the midpoints because we're calling for it, now let's go ahead and write out what is it that I need to show, okay? So according to this theorem right here, or according to this proof right here, I need to show the following. I need to show, number one, that MN, the line segment, is supposed to be parallel to RS, the line segment, because remember, I'm trying to show that they are parallel to each other, as you can see in this picture. So here's MN, and then also RS is on the bottom. In addition to that, number two, I need to show that MN is going to be half the length of RS. And let me go ahead and give ourselves a little bit of space because I think we can do the proof in between them. So part two, I need to show that MN is equal to half of RS. All right, so if I can show those two according to these coordinates, then we're pretty much home free then. Okay, let's go ahead and do to each ones then. If I'm showing that two line segments are parallel to each other, the best way to do it is to show that their slopes are going to be the same. So let's go ahead and solve for the slope then. So the slope of MN is going to be the change of y over the change of x. So that's going to be C minus C divided by A plus B and then minus B, right? Change of y over change of x. So that's going to give me 0 over A. Now I'm going to go ahead and solve for the slope of RS and pray that it's going to be the same thing. So the change of y over the change of x, that's going to be 0 minus 0 divided by 2a minus 0. So that's going to give me 0 over 2a. And even though the bottom is 2a and the other one is a, it's still okay because both of them are equal to 0. So that means that this checks out. So there it is. That's the easier part. Now the second part, hopefully that should be just as easy. We'll find out. This one, we're going to have to probably use the distance formula for it. But if you can probably see it, you can probably figure out what's the length of it according to the picture. The length of RS, right, if you were to just look at it, it's going to be equal to 2a because horizontally you move that much from R to S. But let's just say for the sake of argument that you didn't see that and you want to use a distance formula. So that's going to be the square root of 2a minus 0 quantity squared plus 0 minus 0 quantity squared, and then take the square root of the whole thing. So the square root of 2a quantity squared, so that's equal to 2a. So if you ever use the distance formula and it's not horizontal, that's the path that you want to take. Now, if I do the same thing for mn, let's just see what happens then. So mn right there, I need to use the distance formula. And if you don't see that's horizontal, well, then just use what we just said. So let's see, that's going to be a plus b minus b quantity squared. That's the change of x. And then for the other part over here, it's going to be c minus c quantity squared, and then that's going to give you 0. So inside, you're going to have a squared because b cancels out and the c's also cancel out. So that gives you a length of a. So right there, you can see that since one is equal to 2a, the other one is equal to a, then that means that's exactly what I want. And therefore, mn is equal to 1/2 of rs. So there's your proof, right? A lot easier in this case. Okay, let's look at one last example in this one, okay? And then I think we'll go ahead and call it then. Prove that in a parallelogram whose diagonals are going to be perpendicular to each other, that's going to give you a rhombus, okay? Prove that if you have a parallelogram whose diagonals are perpendicular to each other, then the result is a rhombus. So since we worked off of earlier, since we created a parallelogram earlier, over here, why don't we do exactly the same thing then? If you would like to pause the video and try this for yourself, that's totally fine. You know, that's definitely worth trying if you can. So if not, then I'm going to go ahead and get started. Okay, so first I'm going to go ahead and use the origin once again, 0, 0. Then I'm going to go over here. We're going to create another point. We're going to go ahead and call that a comma 0. Then for over here, we're going to go ahead and use another coordinate over here, which we're going to go ahead and call BC. And if you remember, for the other one over here, then that's going to be B plus A comma C. So that was our parallelogram from problem number 1. Now, again, if you want, you can go ahead and double each one. But since I figure, you know, since we work with number 1, we'll just go ahead and work with what we have right here. Okay, so let's go ahead and draw our parallelogram, right? And I guess I should draw this a little bit better right here. So that's going to be A. And I do believe that we were using RUST or RSTU in this case. So let's go ahead and use the same thing. So here's R, and then here's S, and then here's T, and then here's U. So the first part is in the if statement, we know that US is supposed to be perpendicular to TR. So that means that's part of the given. So given that US is perpendicular to TR, I need to show that that right there, RSTU, is a rhombus. And by definition, the rhombus means that all of the sides are going to be congruent to each other. All right, so let's see how we can pull this off. Now, knowing that US is perpendicular to TR, perpendicular, the key word right there, is basically referring to the slope, right? And anytime you're talking about perpendicular, I think the slope should be involved. So let's go ahead and do that then. So first what I'm going to do is I'm going to go ahead and set up the slope for US in this case, okay? So the slope for US, and here's the line segment US over here, okay? The slope is going to be 0 minus C divided by A minus B. Okay, so that's going to be the slope for US. And if you want to clean that up, that's negative C divided by A minus B. All right, now I'm going to go ahead and do the same thing for RT over here. Okay, so I'm going to go ahead and solve for the slope of RT. So the slope of RT is going to be C minus 0 divided by B plus A. So if I clean that up, that's C over A plus B. Okay. Now, since we know that the two are supposed to be perpendicular to each other, then that means that their slopes are supposed to be negative reciprocal of each other. Okay. So since the slope of since US is perpendicular to TR, then that means that the slope of US is equal to the negative reciprocal of the slope of TR. Okay, so let's go ahead and set that up then. The slope of US, that is going to be negative C divided by A minus B. And then for the other part, I also have the negative of 1 over the slope of TR. The slope of TR, that's going to be C divided by A plus B. And at this point, we're going to have to kind of play around with the algebra a little bit just to see what happens. Okay, that happens, quite often. All right, so let's see. The reciprocal of a fraction, well, then we're just going to have to flip the fractions. So that means negative C over A minus B is equal to A plus B divided by negative C. So we're just kind of take that fraction and flip it over. And I think that at this point, the only thing I can do is cross multiply just to see what happens. So C squared, because the negatives are canceling out, is equal to A plus B multiplied by A minus B. Okay, A plus B times A minus B, that's the difference of square. So that's equal to A squared minus B squared is equal to C squared. And I think we're at this point going to be kind of like at a dead end because we can't really do too much. So we have, I guess, A squared is equal to B squared plus C squared, which is pretty much the end. And this right here is something that we're going to have to translate as to how is this all going to work out. Well, according to our picture, now the question is, what is this going to do for us? We know that we need to show that RSTU is supposed to be a rhombus. And by definition, that means that all the sides are congruent to each other. I can definitely see that this length right here is equal to A because of, using the distance formula, and because it's horizontal, you can see how that works. And over here, we said earlier, that's also equal to A because, well, it's exactly the same thing. Now, the question is, what is this length over here, which is going to be RU? Well, we are trying to find a distance from R to U over here, so we can use the distance formula. RU is supposed to be equal to, according to the distance formula, the square root of B squared plus C squared, because it's the change in the X value squared plus the change in the Y's value squared. If you want here, we can just kind of write it all out just so you can see it. So B minus 0 squared, and then plus C minus 0 squared. But more importantly, what's going to happen is if I clean that up, you're going to get the square root of B squared plus C squared. And look at what we have earlier. From earlier, we said that B squared plus C squared is equal to A squared. So I can go ahead and plug that in, and that's going to give me the square root of A squared, which tells me then that length is also equal to A. Now, finally, if I solve that for TS, I'm pretty sure that's going to give me the same thing. So let's just go ahead and seal the deal for this one. So TS right here, using the distance formula, is supposed to be B plus A minus A quantity squared plus C minus 0 squared. And lo and behold, if you notice, the inside is also equal to B squared plus C squared. So we can replace that with A squared, and then therefore the length is A. So therefore, now RU is equal to TS, which is equal to RS, which is equal to the last length, which is UT, and they're all equal to A. So therefore, this is going to be a rhombus then. All right, so there you go. Thank you so much for watching. Hopefully this is going to be somewhat insightful. And I got one last thing before you guys go, and here it is. All right, need to sneak that in. All right, take care, everybody.